Welcome to the module on the applications of recycled batteries. In this module, we will review the key results. Batteries are classified as primary or secondary, depending on their ability to be recharged. Primary batteries, or disposable types, are single-use and valued for their long shelf life and portability, making them ideal for low-power devices like remotes, clocks, toys, and hearing aids. Common examples include alkaline, zinc carbon, and lithium primary batteries. Secondary batteries, or rechargeable types, can be reused multiple times and are essential for high-energy applications such as electric vehicles, portable electronics, and energy storage systems. These include lead-acid, nickel-cadmium, nickel-metal hydride, and lithium-ion batteries, supporting the shift toward a sustainable, electrified future. Batteries power modern technologies from electronics to electric vehicles and energy storage systems. Yet, their growing use brings environmental and resource challenges. Effective recycling is essential to recover valuable materials like lithium, cobalt, nickel, and manganese, reducing waste and dependence on raw mining. Battery recycling supports a circular economy, lowering production costs, preventing pollution, and conserving resources. However, widespread adoption remains limited by technological and economic barriers. Advancing recycling systems is key to achieving a sustainable and resource-efficient energy future. Recycling technologies are vital for managing battery waste sustainably and recovering valuable materials. As rechargeable batteries, such as nickel-cadmium, nickel-metal hydride, and lithium-ion, become more widespread in electronics and electric vehicles, the number reaching end of life continues to rise, creating environmental and resource challenges. Recycling helps recover critical metals like nickel, manganese, cobalt, and lithium, reducing waste, cutting reliance on mining, and supporting a circular battery economy. These recovered materials can be reused in new battery production, closing the loop in the value chain. Further innovation is needed to improve the recovery of other components, including graphite, electrolytes, and plastic separators, to achieve a more sustainable and resource-efficient energy future. Before recycling or disposal, spent batteries must undergo pre-treatment to separate their components safely and efficiently. This process enhances material recovery, lowers energy consumption, and reduces environmental risks during recycling. Pre-treatment also addresses major safety hazards, including electrical shocks, fire or explosion risks, and chemical exposure, which increase with higher battery energy densities. Key pre-treatment steps include sorting, discharging, dismantling, mechanical treatment, sieving, separation, and thermal or chemical processing. These operations ensure safe handling and prepare materials for efficient recovery in later stages. Together, they establish the foundation for a safe, effective, and sustainable battery recycling system. Spent batteries after the pre-treatment are treated using three main recycling routes: pyrometallurgy, hydrometallurgy, and direct recycling. Each method is tailored to the specific battery chemistry and the desired products, and in practice they can also be combined in hybrid process flows. Pyrometallurgy uses high temperatures to produce metal alloys and slag, hydrometallurgy relies on aqueous chemistry to selectively recover metals, and direct recycling aims to restore cathode materials for reuse with minimal chemical change. Choosing recycling methods that match the degradation behavior and failure modes of battery materials can significantly improve recovery efficiency, reduce processing costs, and cut environmental emissions. Pyrometallurgy relies heavily on the chemical reaction of ores with other elements or compounds at high temperatures to refine metals. This method is one of the traditional metallurgical methods, which is widely used to refine various metals, including copper, iron, nickel, and lead, and is a commonly used technology in the metallurgical industry. The pyrometallurgical steps are the same, but the exact process, temperatures, fluxes, furnace type, gas handling, and product streams, is customized to each battery chemistry and the target metals. Hydrometallurgy is a promising recycling method due to its low energy consumption and ability to recover a wide range of valuable metals. Taking advantage of dissolving metals in aqueous media, hydrometallurgy holds significant appeal for battery recycling due to its cost-effectiveness, minimal energy consumption, temperatures less than 100 hollow bullet C, and low environmental footprint. The two phases of this technique include the leaching batteries and the recovery of high-value components from the leachate. In the leaching process, various chemical reagents, such as acids or alkalis, are used to dissolve the metal ions from the battery waste. After leaching, separation and purification techniques are used to remove impurities and isolate the metal ions for further processing. After hydrometallurgy, additional processing or refining steps, such as precipitation, solvent extraction, ion exchange, or electrolysis, may occur. Direct recycling focuses on recovering the active materials from batteries without destroying their crystal structure. First, lithium-ion batteries are disassembled and physically separated, for example by magnetic separation and mild thermal treatment, to protect the cathode powders. The recovered powders then go through purification and repair. Their structure and lithium content are restored using methods such as hydrothermal treatment, slurry in an autoclave with a lithium source, solid-state annealing, electrochemical re-lithiation, or chemical re-lithiation in solution. The objective is to produce regenerated cathode materials that can be directly reused in new cells. Direct recycling is mainly developed for lithium-ion batteries because their cathode materials are high value and structurally recoverable. Conventional smelting or full hydrometallurgy would destroy this structure and lose part of that value. Lithium-ion batteries contain high-value materials such as lithium, nickel, cobalt, manganese, copper, aluminum, and graphite. Through recycling, many of these metals can be recovered and fed back into the battery supply chain, reducing the need for primary mining and lowering environmental impacts. Lead-acid batteries are one of the most successfully recycled products worldwide, with recovery rates often above 95%. Their simple and robust design enables an efficient, closed-loop system where lead, plastic casings, and even sulfuric acid can be recovered and reused in new batteries. Nickel-based batteries, including nickel-cadmium and nickel metal hydride, are important in applications such as power tools, backup systems, and hybrid vehicles, and they contain high-value metals like nickel, cobalt, cadmium, and rare earth elements. Because these metals are critical and energy-intensive to mine, recycling nickel-based batteries is increasingly important for resource security and environmental protection. Modern recycling processes combine mechanical pretreatment with pyrometallurgical and hydrometallurgical steps to recover nickel, cobalt, cadmium, and rare earth elements, allowing these materials to re-enter the value chain instead of being lost in waste streams. Recovered materials from end-of-life batteries can be repurposed across multiple sectors, including the manufacture of new batteries, electronic parts, and other energy storage technologies. In many instances, recycling can impose a smaller environmental burden than producing metals through mining and ore processing. Metals such as cobalt, nickel, and lithium can be refined and fed back into battery production, while materials like graphite can be redirected into lubricants and other carbon-based products. Recovered fractions may also be used to produce ceramics, glass, and other industrial materials. Overall, this reuse both preserves natural resources and limits the environmental impacts tied to extracting and processing virgin feedstocks. However, despite numerous proposed pathways for replacing primary raw materials with secondary ones, there remains a substantial gap between research activity and real-world reuse at scale. This disconnect persists even though such secondary materials are often labeled sustainable because they originate from recycled waste. Consequently, any proposed recycling route should be assessed rigorously to confirm its true sustainability and practical value. Battery recycling significantly reduces environmental pollution, conserves natural resources, and lowers the carbon footprint of energy storage technologies. To fully realize these benefits, advancements in recycling technologies, improved collection systems, and strong regulatory frameworks are required to support a sustainable and circular battery economy. Battery recycling can generate significant economic value by lowering raw material costs, reducing environmental liabilities, and supporting domestic supply chains. While lead-acid battery recycling is already economically robust, lithium-ion and nickel-based battery recycling require continued technological innovation, supportive policies, and market development to fully realize their economic potential within a circular battery economy. Batteries recycling faces system-level challenges across the full chain. Collection is still insufficient and battery diversity makes sorting and identification difficult, which can reduce recovery and increase safety and environmental risks. Disassembly remains labor-intensive and hazardous due to residual charge and flammability, while policy gaps and limited standardization hinder traceable, regulated recycling. Finally, many technologies are still scaling from lab, pilot to industrial operation, where consistent feedstock supply, automation, and validated emissions cost data are critical for sustainable deployment. In summary, recycling has become crucial to manage waste, conserve resources, and recover valuable materials. Recycling supports a circular battery economy, reducing dependence on raw material mining and minimizing environmental pollution. Spent batteries are treated using three main recycling routes: pyrometallurgy, hydrometallurgy, and direct recycling. Each method is tailored to the specific battery chemistry and the desired products, and in practice they can also be combined in hybrid process flows. Battery recycling and mining become essential tools to recover valuable metals, reduce dependence on raw materials, lower costs, and support a more sustainable, resource-efficient battery economy. Finally, to achieve high recycling rates at a competitive cost and to meet the growing demand for batteries, significant innovation is needed in integrating existing recycling methods for batteries. This will require a collaborative effort from policymakers, researchers, and industry players to overcome the challenges and make recycling more efficient, safe, and sustainable. Thank you for your attention.